Hello, and thank you for joining me on this journey. Tonight, we will slowly drift into the quiet hum of human innovation, exploring the hidden currents of energy that have shaped our world. Imagine the first sparks of electricity flickering from early dynamos, the rhythmic turning of turbines in coal-fired power stations, and the soft glow of street lamps illuminating cities long before modern skyscrapers. Let your mind wander through the invention of power plants, the delicate balance of hydroelectric rivers, and the silent force of nuclear energy holding its calm within steel walls. Picture wind and solar farms stretching across distant landscapes, and the faint digital pulse of smart grids carrying power invisibly through towns and cities. If you enjoy these relaxing moments, please consider leaving a like, subscribing, and turning on all notifications so you don't miss any of our future videos. But for now, just breathe. Let your body relax, release any tension, and allow your mind to drift. Let's begin. In the dim glow of candlelit laboratories, the air hung thick with the scent of oil lamps and the faint tang of metals warmed by experimentation. It was a time when the world, still draped in the slow rhythm of horse-drawn carriages and gas-lit streets, began to sense the invisible forces threading through the air around it. Electricity, a phenomenon known yet scarcely understood, became a source of fascination for those willing to chase sparks across copper wires and glass globes. In the early 19th century, minds such as Benjamin Franklin gazed skyward during thunderstorms, kite strings trembling with potential, pondering the very nature of lightning and the invisible currents that danced from cloud to earth. Laboratories were sanctuaries of meticulous observation, where Michael Faraday, among others, traced the delicate interplay between magnets and coils of copper wire. With each measured rotation of a magnet through a coil, the faintest glow of induced current appeared, like a whisper from the natural world, hinting at forces that could one day drive machines, illuminate streets, and animate factories. These discoveries were at once scientific and almost mystical, the invisible made manifest in tiny arcs of light that flickered over polished brass and glass instruments. The inventors of this era were guided not solely by logic, but by an almost artistic curiosity. They observed how Leyden jars could store charge, how simple circuits could send energy across small gaps, and how sparks leapt from conductor to conductor in a manner that seemed alive. Each small revelation carried a weight of promise, suggesting that these delicate, unseen forces might one day power more than just experiments. They might illuminate the world. The act of invention was a slow, deliberate choreography of patience and intuition. Amid these sparks of discovery, society began to stir with anticipation. Public demonstrations of electrical marvels drew crowds, their faces illuminated by flickering arcs, reflecting awe and trepidation. The novelty of electric light, the gentle hum of a motor, the sudden flash of a spark, all these sensations intertwined with a growing cultural fascination with light, motion, and power. In some ways, electricity became a language of wonder, a silent conversation between humanity and the forces of nature, inviting experimentation and observation. Rivalries emerged too, as inventors competed to harness these forces most effectively, each spark igniting both imagination and ambition. Faraday's experiments, methodical and precise, planted the seeds for electromagnetic induction, the principle by which power could flow from one coil to another. This principle, quietly profound, would one day form the backbone of dynamos and generators, enabling energy to be transported, stored, and applied on scales previously unimaginable. In parallel, the cultural resonance of these early experiments, lights glowing in parlors, instruments buzzing in workshops, threaded electricity into the fabric of daily life, long before cities hummed with fully operational power grids. In imagining these early days, one sees a world poised between curiosity and transformation. Candle flames trembled beside rudimentary motors. Brass fittings and glass tubing reflected the eyes of inventors as they leaned in, observing, adjusting, and documenting. Each spark was a whisper of what was to come, an invitation to consider the unseen forces shaping matter and motion. The first power plants were not yet conceived, but the foundation was laid. A fusion of intellect, creativity, and careful experimentation that would propel humanity into an age of light and energy. And so, the birth of electrical curiosity was both a personal and collective awakening. From small-scale experiments to the first glimmers of urban electrification, the early 19th century was a period of subtle revelation. Sparks flitted across wires, and the world took note, not with immediate understanding, but with a sense of potential that would unfold over decades. In these shadowed rooms, amidst coils, magnets, and jars of electricity, the imagination of humanity stretched toward a future where energy could be harnessed, shaped, and shared, illuminating not only streets and homes, but the very possibilities of progress itself. Morning mist clung to the edges of industrial towns, curling around the chimneys and steel frameworks of buildings that seemed to stretch endlessly toward the sky. The Industrial Revolution had transformed not only machinery, but the very heartbeat of human life. And nowhere was this more evident than in the emergence of the first coal-fired power stations. Steam engines, vast and intricate, churned beneath vaulted roofs, their pistons compressing and releasing in steady rhythm, driving dynamos that hummed with the promise of light. The smell of burning coal, heavy and persistent, mingled with the metallic scent of machinery, forming an atmosphere both oppressive and exhilarating, signaling the birth of a new age of energy. Across factory floors, engineers adjusted valves and monitored gauges, translating theory into functioning systems. Steam generated in massive boilers was carefully directed toward turbines, the force of pressurized water turning blades that rotated generators with mechanical grace. These early plants were feats of both engineering and vision, marrying scientific understanding with the demands of urban life. Streets began to glow under electric lamps, and homes that once relied on oil or gas light flickered with a new, more consistent illumination. The presence of electricity, produced by the combination of steam and coal, reshaped daily life with a subtle yet pervasive energy, linking industry to households and communities. In examining the evolution from experimental generators to fully operational stations, one observes the meticulous attention required to harness such immense power. Early engineers studied heat transfer, fluid dynamics, and electromagnetic principles, applying knowledge incrementally to scale from laboratory curiosities to functional urban infrastructure. The first dynamos, often mounted on wooden frames and driven by belts and pulleys, served as prototypes for larger, more durable machines. By integrating coal combustion and steam turbines, engineers created systems capable of sustaining continuous electricity. lighting not only factories, but streets, offices, and residential neighborhoods. The physical structures themselves embodied ambition. Brick and steel towers rose above industrial districts, while conveyor systems and chutes funneled coal from storage bunkers to furnaces. Smoke curled into the sky in slow, deliberate plumes, shaping both the aesthetic and the practical identity of these emerging power hubs. Within, networks of copper wiring spread across ceilings and walls, connecting switches, meters, and generators, forming the earliest electric grids. Though rudimentary compared to contemporary systems, these networks represented a foundational step toward interconnected urban energy, demonstrating the transformative potential of centralized power production. Workers played a crucial role, their labor both careful and continuous. Monitoring the pressures in boilers, adjusting steam valves, and inspecting mechanical linkages demanded constant vigilance, as even minor fluctuations could compromise efficiency or safety. The orchestration of human skill and mechanical energy mirrored the larger societal shift toward industrialization, emphasizing coordination, resilience, and technical expertise. Communities that grew around these plants experienced profound change, with electricity enabling longer working hours, expanding production capabilities, and altering patterns of social life. The technical evolution of these stations was matched by cultural fascination. Cities illuminated by electric light became symbols of progress, a visible testament to the capacity of human ingenuity to reshape the environment. Scientific knowledge and practical engineering merged, as turbines driven by steam provided a new scale of energy previously unimaginable in urban centers. The transition from local experimental generators to centralized power plants reflected a growing understanding of energy management, demonstrating how coal and steam could be harnessed not only for individual machines, but for entire networks serving populations and industries. By the end of the 19th century, these monumental constructions had become the backbone of modern urban existence. Streets, factories, and homes benefited from reliable illumination, while engineers refined techniques for turbine efficiency, boiler operation, and grid integration. The first coal-fired power plants laid the foundation for larger, more sophisticated stations to come, signaling an era where energy availability began to dictate economic and cultural development. As steam-powered turbines whirred and coal-fired flames burned steadily beneath steel boilers, the world witnessed a pivotal convergence of curiosity, technical mastery, and social transformation. A moment when the harnessing of energy began to define the rhythm of cities and the trajectory of civilization. In the bustling streets of late 19th century America, gas lamps flickered as horse-drawn carriages clattered past buildings that would soon glow with a new brilliance. At the forefront of this transformation stood Thomas Edison, a relentless inventor whose insistence on direct current shaped the early vision of electrical distribution. Edison's approach relied on low-voltage networks that could illuminate homes and factories within a limited radius, favoring safety and simplicity over long-distance transmission. His incandescent bulbs, housed in small filaments of carbon encased by glass, brought a steady, manageable light that seemed magical to those accustomed to flickering oil lamps. Elsewhere, a different vision of energy was unfolding. Nikola Tesla, a brilliant engineer and visionary, championed alternating current, which could traverse greater distances with reduced energy loss. Tesla's collaboration with industrialist George Westinghouse challenged Edison's philosophy, creating a rivalry that would become one of history's most dramatic scientific confrontations. AC systems employed transformers to step voltage up and down, enabling electricity to be transmitted efficiently across towns, cities, and eventually entire regions. The conceptual leap allowed for the construction of larger power stations and networks, demonstrating that energy could flow far beyond the limits of a single neighborhood or factory. The war of currents was not merely technical, but also public. Edison conducted demonstrations intended to illustrate the dangers of high-voltage AC, including the unfortunate electrocution of animals in staged settings, emphasizing the perceived risks to a society still becoming acquainted with electricity. Tesla and Westinghouse countered with evidence of AC's advantages, highlighting the efficiency and scalability of alternating current for powering the growing industrial and urban landscape. These battles of persuasion and engineering unfolded alongside the development of large-scale generators, transformers, and distribution lines that formed the skeleton of modern electrical grids. Industrial application of both DC and AC systems transformed cities in tangible ways. Factories extended their operating hours as electric light replaced gas and oil. Streets became safer and more navigable at night, and urban centers grew more interconnected. The hum of generators, the click of switches, and the subtle glow of electric arcs became part of the sensory fabric of urban life. Engineers refined motor designs, motors that could drive machinery and transport systems while lighting networks, allowed businesses and homes to experience a newfound consistency in illumination. Tesla's alternating current found its most celebrated application in large hydroelectric plants, such as those at Niagara Falls, where mechanical energy from water was converted into electricity, capable of supplying multiple cities simultaneously. The installation of turbines, transformers, and high-voltage transmission lines demonstrated the practical superiority of AC for long-distance delivery, cementing its role in the expansion of national energy networks. Edison's DC systems continued to serve local applications, providing reliable service in factories and neighborhoods where voltage losses over distance were minimal. Beyond the engineering feats, this era highlighted the interplay between innovation and ambition. Rivalries drove experimentation at unprecedented speed, resulting in technological breakthroughs that would define the modern world. The spectacle of electric lights illuminating streets, public squares, and expositions captured the imagination of the public, symbolizing progress and the transformative power of scientific understanding. Each spark of invention, each prototype generator, and each new installation added to a growing infrastructure that linked knowledge, energy, and human society. By the close of the 19th century, the triumph of alternating current had enabled cities to expand, industries to scale, and people to experience electricity on a larger scale than ever before. Yet the contributions of both Edison and Tesla were integral, reflecting a period when bold ideas clashed and complemented one another, producing the frameworks upon which modern electrical grids now rely. The war of currents, marked by rivalry, ingenuity, and vision, illustrated that the flow of electricity was as much a human story as it was a technical one, a narrative of imagination, determination, and the enduring quest to illuminate the world. Steel girders stretched across expansive halls, their polished surfaces reflecting the rhythmic motion of colossal steam turbines. As the 20th century unfolded, electricity shifted from the confines of modest local generators to the sprawling scale of industrial power stations. Steam turbines, designed with precision and operated with care, replaced smaller engines, converting high-pressure steam into mechanical rotation capable of driving generators of immense capacity. The mechanical elegance of these facilities was matched by their societal impact as urban centers expanded and the demand for reliable, large-scale energy grew alongside industrial ambition. From the base of a turbine hall, one could hear the measured turning of shafts and the resonant vibration of massive bearings. Engineers monitored the alignment of blades, regulated the input of steam from high-pressure boilers, and observed instrumentation that recorded torque, rotational speed, and electrical output. Each component worked in concert, an intricate orchestration of mechanics and thermodynamics. The scale of these operations allowed a single plant to provide power for entire districts, a leap forward from the small localized networks of earlier decades. Innovation within turbine technology reshaped industrial workflows. Factories could now operate more efficiently, with machines running longer hours under the continuous energy supplied by robust turbines. Electrically driven equipment replaced some steam-powered machinery, reducing the complexity of transmission systems within buildings and allowing for more compact, flexible plant layouts. The shift towards centralized turbines also enabled engineers to manage energy with greater consistency, improving voltage stability and supporting higher capacity generators. These technical refinements echoed the pioneering work of Edison and Tesla, translating the principles of electricity into scalable, practical infrastructure. The architectural design of turbine halls emphasized both utility and scale. Vaulted ceilings accommodated tall turbine shafts, while steel beams and reinforced concrete absorbed vibrations and supported heavy machinery. Walkways and observation platforms allowed operators to access gauges and monitoring equipment safely, bridging human oversight with mechanical operation. Coal-fired boilers or oil-fired furnaces delivered a steady flow of high-pressure steam, and condensers returned water for reuse, reflecting careful attention to efficiency and conservation. These facilities became landmarks of industrial power, towering above cityscapes and signaling progress through their sheer presence. Workers within these plants assumed roles that required precision, timing, and coordination. Boiler attendants ensured fuel delivery was consistent. Turbine engineers balanced rotational forces, and electricians maintained connections between generators and distribution networks. Safety protocols evolved alongside technology, recognizing the immense energy involved and the potential hazards of misalignment, overheating, or overpressure. The daily rhythms of the plant reflected a harmony between human skill and mechanical reliability, with the hum of turbines marking the pulse of urban life. The effects of large-scale turbines extended beyond the plant itself. Cities experienced new patterns of illumination, with streetlights and commercial buildings powered more steadily and extensively than before. Industry benefited from reliable energy capable of sustaining machinery that previously required intermittent operation or decentralized steam engines. Economies expanded as manufacturing could occur at higher volumes and with greater precision, fostering urban growth and supporting population increases. The integration of turbines into energy infrastructure represented a convergence of scientific understanding, engineering expertise, and societal demand. By tracing the evolution of these massive machines, the continuity of electrical development becomes apparent. The early experiments of Faraday, the innovative designs of Edison and Tesla, and the first coal-fired power stations all contributed foundational knowledge that enabled the scale and reliability of modern turbines. Steam-driven generators set a precedent for subsequent advances, including hydroelectric and later renewable energy technologies, demonstrating that the principles discovered in small laboratories could be amplified to meet the needs of entire cities. Each revolution of a turbine blade signaled more than mechanical motion. It embodied the transformation of energy into an essential driver of human progress, shaping both the industrial landscape and the daily experience of civilization. Water, ever flowing, carries both the passage of time and the potential for energy. From the early 20th century onward, engineers and visionaries began harnessing the force of rivers to generate electricity, creating hydroelectric plants that transformed natural landscapes and human settlements alike. Dams, reservoirs, and spillways reshaped valleys, redirecting currents to drive turbines capable of producing immense and reliable power. Unlike coal-fired plants, these facilities relied on the ceaseless rhythm of water rather than combustion, offering a renewable source of energy that could sustain cities, factories, and industries with minimal interruption. In the control rooms of these early hydroelectric stations, operators monitored gauges recording water levels, flow rates, and turbine speed. High above, penstocks funneled water from reservoirs to the blades of turbines, converting gravitational energy into mechanical motion. Generators connected to these turbines transformed rotation into electricity, sending voltage along transmission lines to distant communities. The motion of water, visible and tangible, became an instrument of energy production, its force harnessed with precision to serve society. Engineers studied hydrodynamics and materials science to ensure structures could withstand seasonal floods, sediment accumulation, and the immense pressure exerted by millions of gallons of water. Hydroelectric development required both technical insight and a willingness to reshape the natural world. Valleys were flooded to create reservoirs, redirecting rivers and submerging landscapes that had existed for centuries. Forests, farmlands, and even small settlements were relocated or lost beneath expanding bodies of water. While these changes allowed electricity to be produced on an unprecedented scale, they also transformed ecosystems, altering habitats and influencing the flow of nutrients, sediments, and aquatic species. The balance between human utility and environmental impact became an ongoing consideration, one that continues in contemporary energy planning. The architectural forms of dams and powerhouses were as much a statement of human ingenuity as they were functional structures. Concrete walls soared across riverbeds. Spillways directed excess water with calculated precision, and turbine halls contained massive rotating machinery designed to withstand constant hydraulic pressure. Observation galleries allowed engineers to inspect turbines and adjust mechanical linkages, while control panels regulated voltage and monitored generator performance. Each component was calibrated to maximize efficiency, protect structural integrity, and ensure consistent energy output for growing populations. Communities adjacent to hydroelectric plants experienced dramatic shifts in daily life. Electricity became available in areas previously unreachable by conventional power grids, enabling expanded industrial activity, improved lighting, and enhanced domestic conveniences. Economies adapted to new energy availability, with factories able to operate larger machinery and towns benefiting from increased connectivity. Rivers, once simply a source of transportation or irrigation, were transformed into engines of societal progress. Their flow measured not only in cubic meters per second, but in the illumination and productivity they made possible. Hydropower also illustrated the interplay between natural forces and human engineering. Seasonal variations in rainfall and snowmelt required careful reservoir management, while turbines and generators needed regular maintenance to handle fluctuating water pressure. Innovations in turbine design, from Francis to Kaplan models, allowed plants to operate efficiently across diverse river conditions, demonstrating the adaptability of technology to environmental circumstances. The serene surface of a reservoir belied the complexity of energy conversion occurring below, where blades spun, generators produced electricity, and control systems balanced mechanical and electrical loads with precision. Through the creation of hydroelectric infrastructure, the 20th century witnessed a new vision of energy production, one that linked human ingenuity to the power of natural resources. The interaction between rivers and turbines provided abundant electricity while introducing considerations of ecology, engineering, and community planning. These plants, visible across valleys and mountains, remain monuments to both technical achievement and environmental transformation, marking the convergence of flowing water and human ambition, and setting a precedent for sustainable approaches to electricity generation in subsequent generations. Beneath the steel and concrete shells of nuclear power plants, an extraordinary transformation occurs at the scale of atoms. By the mid-20th century, scientists had learned to release the energy contained within atomic nuclei, converting it into electricity with efficiency and density unmatched by fossil fuels or hydroelectric systems. Nuclear fission, the splitting of uranium or plutonium atoms, produces immense heat, which is then harnessed to generate steam that drives turbines. The principle is deceptively simple, yet the engineering required to control it safely is among the most sophisticated in human history. Inside reactor halls, control rods move methodically, absorbing neutrons to regulate the chain reaction. Coolant circulates through the core, transferring heat to water in steam generators. Operators monitor gauges, temperature sensors, and pressure valves, ensuring that each system maintains equilibrium. The hum of pumps, the hiss of pressurized fluid, and the glow of instrument panels create an atmosphere of constant vigilance and precision. Each action, from adjusting rod insertion to balancing thermal loads, contributes to a controlled release of energy that powers cities without the combustion of fuel. Nuclear plants introduced a new scale of energy density. A relatively small amount of uranium could provide electricity for months, reducing the need for massive fuel supplies and minimizing the footprint of energy storage compared to coal or oil. Cooling towers, rising above plant complexes, release steam that blends with the sky, signaling the transformation of atomic energy into forms perceivable by human senses. These towers, often cylindrical and monumental, reflect both functional necessity and the symbolic presence of a new power source that reshaped the energy landscape. The development of nuclear energy carried profound social and political implications. Public perception was a mixture of hope and apprehension, influenced by both the promise of abundant, low-carbon electricity and the memories of wartime applications of atomic technology. Engineers and physicists worked not only to generate energy efficiently, but to communicate safety protocols, environmental impacts, and emergency procedures to regulators and communities. This dual role of innovation and stewardship became a defining feature of nuclear power, as operational excellence was inseparable from societal trust. Technological refinement advanced rapidly. Early reactors, such as those designed for research or experimental energy production, evolved into larger commercial units capable of supplying entire regions with continuous electricity. Redundant safety systems, multiple cooling circuits, and robust containment structures reduced the risk of accidents, while instrumentation allowed for precise monitoring of neutron flux, heat transfer, and electrical output. The combination of physics, materials science, and mechanical engineering converged to create plants capable of running for decades with minimal human intervention, demonstrating reliability on a scale previously unattainable. Beyond the technical achievements, nuclear energy influenced urban and industrial growth. Regions with access to nuclear-generated electricity could expand manufacturing, research, and residential development without dependence on fluctuating fossil fuel supplies. Grid operators integrated nuclear power into broader networks, complementing coal, hydroelectric, and later renewable sources, providing a foundation for stable, high-capacity energy distribution. The presence of nuclear plants shaped both landscapes and economies, reflecting a new confidence in harnessing fundamental forces of nature for human benefit. From the laboratories that unlocked fission to the sprawling reactor complexes supplying megawatts to cities, the atomic era represents a pivotal chapter in energy history. The controlled splitting of atoms brought unprecedented density, continuity, and efficiency to electricity generation, linking scientific achievement with societal transformation. Nuclear energy, through careful engineering and rigorous management, became not only a technical marvel, but a catalyst for broader progress, demonstrating humanity's ability to convert the building blocks of matter into power that fuels civilization. Billowing chimneys traced patterns across the evening sky, a testament to the enduring power of coal, oil, and natural gas. For over a century, these fossil fuels have supplied the steady, reliable electricity that underpins industrial activity, urban life, and modern economies. Coal-fired plants, with their vast boilers and rotating turbines, convert stored chemical energy into mechanical motion and, subsequently, electrical energy. The combustion of coal produces high-pressure steam, which drives generators capable of sustaining entire cities, while the rhythmic movement of turbines provides a continuous hum of industrial vitality. Gas and oil-fired power stations introduced a complementary method of electricity generation. In these plants, combustion turbines convert the energy of burning hydrocarbons into rotational force, producing electricity on both large and intermediate scales. Natural gas, with its cleaner burning characteristics, became a favored fuel in urban areas, where emissions and air quality considerations were critical. engineers developed systems to monitor combustion efficiency, regulate pressure, and manage thermal output, ensuring a controlled release of energy that could respond flexibly to fluctuations in demand. The infrastructure surrounding fossil fuel generation has influenced the shape of human settlements and industrial networks. Railways, pipelines, and ports facilitated the transportation of coal, oil, and gas to plants, while storage facilities and handling equipment allowed continuous supply to maintain uninterrupted electricity. Workers specialized in boiler management, turbine supervision, and fuel logistics, applying technical expertise to sustain energy production. Each plant required a coordinated combination of mechanical skill, chemical knowledge, and operational oversight to maintain efficiency and safety, linking human effort to the large-scale transformation of natural resources into usable power. Fossil fuels also molded cultural and economic landscapes. Urban centers grew taller and more densely populated as dependable electricity supported lighting, manufacturing, and communication systems. Factories expanded operations, taking advantage of reliable, high-capacity energy to run machines for longer hours and at higher productivity. Homes benefited from modern appliances and improved heating, reshaping daily life and domestic routines. The convenience and abundance of electricity generated from coal, oil, and gas became a defining feature of modern civilization, reinforcing patterns of industrialization, economic growth, and technological advancement. Environmental considerations emerged alongside these developments. Combustion produces carbon dioxide, particulate matter, and other emissions that impact air quality, climate, and ecosystems. Engineers and policymakers began implementing controls such as scrubbers, filters, and emission standards to mitigate these effects. The tension between energy availability and environmental stewardship has shaped both technological innovations and policy decisions, driving the gradual shift toward cleaner fuels, higher efficiency, and integrated energy strategies. Fossil fuel power, while abundant and adaptable, demanded careful management to balance human benefit with ecological consequences. Technological innovation in fossil fuel plants continued throughout the 20th century. Turbine design, combustion optimization, and heat recovery techniques increased efficiency, while control systems allowed operators to monitor and adjust output with precision. Combined cycle plants, which use both gas and steam turbines, enhanced energy extraction from fuel, representing a leap forward in reducing waste and maximizing performance. These advances underscored the adaptability of fossil fuel systems, capable of meeting industrial and domestic demands, even as energy consumption expanded worldwide. The story of coal, oil, and natural gas is therefore one of both human ingenuity and reliance on Earth's stored energy. These fuels provided the foundation for modern electrification, supporting urbanization, industry, and technological growth. They exemplify the interaction between resource extraction, mechanical engineering, and societal development, demonstrating how the conversion of chemical energy into electrical power shaped the rhythm of daily life, economies, and civilization at large. Fossil fuel giants, though gradually complemented by other sources, remain a critical chapter in the ongoing history of energy, bridging the past of industrial expansion with the present pursuit of sustainable alternatives. Morning light mingled with the soft glow of electric bulbs, transforming homes and streets in ways that were previously inconceivable. Electricity moved beyond factories and power plants, becoming a companion to daily routines and a silent architect of modern life. Lamps replaced oil and gas lighting, providing steady illumination that allowed households to extend activity into the evening. Kitchens, once dependent on hearth fires, began to integrate electric appliances. Early refrigerators preserved food more efficiently, while simple machines reduced labor and expanded convenience. Offices and commercial spaces evolved alongside residential environments. Typewriters and early electric fans improved efficiency and comfort, while electric lighting created more uniform and controllable illumination than natural daylight or flickering gas lamps. These changes influenced work habits and social patterns, enabling longer hours, safer navigation of indoor spaces, and new possibilities for productivity. Streets lit by electric lamps became safer and more navigable, encouraging evening commerce, public gatherings, and urban mobility in ways that reshaped city life. Public spaces also reflected the transformative power of electricity. Theaters, train stations, and public squares used electric light to enhance architecture and create experiences previously impossible. Illuminated signs and displays communicated information efficiently, while electric trams and streetcars offered reliable, scheduled transportation powered by overhead lines or underground networks. The integration of electricity into both private and public domains fostered a seamless extension of human activity, linking individual homes with larger urban systems. The spread of electricity encouraged curiosity and experimentation at a domestic scale. Families encountered small innovations, from electric irons to vacuum cleaners, each device revealing new ways to manage labor and enhance comfort. Educational institutions benefited as classrooms were illuminated more consistently, supporting reading, writing, and experimentation beyond daylight hours. The presence of reliable energy became a cornerstone of community development, influencing patterns of education, industry, and social interaction. Cultural and social rhythms adapted alongside technological adoption. People adjusted daily schedules to take advantage of lighting and powered appliances, creating a subtle but profound shift in lifestyle. Evening hours, once reserved for rest or simple domestic tasks, were now available for reading, socialization, or creative pursuits. Electricity became a tool not only for efficiency, but also for shaping behavior, expectations, and aspirations, connecting the individual experience with broader societal change. In rural regions, electrification extended opportunities and improved quality of life. Farms and small towns gained access to lighting, powered water pumps, and refrigeration, increasing agricultural productivity and household convenience. Electricity bridged distances between urban and rural areas, enabling communication, commerce, and cultural exchange in ways that enhanced integration and development. From early incandescent bulbs to the first electric appliances, electricity's influence on daily life represents a shift that was both practical and symbolic. It connected human activity to a new dimension of energy, enabling flexibility, efficiency, and expansion of daily routines. The integration of electrical systems into homes, workplaces, and public spaces illustrated the profound ways technology can reshape behavior, culture, and the flow of civilization, preparing the foundation for subsequent innovations in renewable and sustainable power. Across rooftops and open fields, solar panels now gleam, capturing sunlight and converting it into electricity with increasing efficiency. Photovoltaic cells composed of semiconductor materials, absorb photons from the sun and release electrons, creating a flow of current that feeds homes, businesses, and grids. Offshore wind farms extend this principle to the oceans, where massive turbines harness the kinetic energy of moving air, turning blades to generate power. Both solar and wind energy exemplify a transformation from centralized fossil fuel-based systems to distributed renewable networks. Modern energy infrastructure relies on smart grids to manage the integration of these variable sources. Sensors, meters, and digital communication systems continuously monitor production and consumption, balancing supply with demand across regions. Battery storage complements intermittent generation, storing surplus energy during periods of high production and releasing it when sunlight fades or winds calm. This dynamic interaction allows electricity to flow efficiently, reduces waste, and improves grid stability while supporting the growing complexity of urban and industrial electricity usage. Communities experience renewable energy in subtle yet profound ways. Residential solar arrays provide homeowners with the ability to generate a portion of their own electricity, influencing consumption patterns and creating opportunities for energy trading through local networks. Wind farms supply regions with substantial energy input, replacing some reliance on fossil fuels and reducing greenhouse gas emissions. Together, these technologies reshape environmental impact while maintaining the reliability and continuity necessary for modern civilization. Engineering advances make renewable energy increasingly practical. Solar panel efficiency has improved through the use of multi-junction cells, anti-reflective coatings, and tracking systems that follow the sun's path. Turbine design has evolved to include longer blades, higher towers, and materials capable of withstanding extreme weather, increasing power output and durability. Integration into existing electrical systems requires careful planning, as energy from renewable sources must be synchronized with traditional grids, using inverters, transformers, and monitoring systems to maintain stable voltage and frequency. The adoption of clean energy reflects a broader cultural and economic shift. Governments, utilities, and private enterprises invest in infrastructure that supports sustainable production, often incentivized by policy, environmental awareness, and global climate considerations. Public perception of energy has shifted from simple availability to responsibility, linking human activity with ecological consequences. Renewable energy projects demonstrate the possibility of maintaining societal growth while mitigating environmental disruption, presenting a model for energy systems that align technology with stewardship of natural resources. As energy networks evolve, digital intelligence plays a pivotal role. Smart grids allow for predictive demand management, real-time monitoring of generation sources, and automated distribution adjustments. Data analytics help anticipate fluctuations in production and consumption, enabling operators to optimize efficiency and integrate diverse energy types without compromising service quality. This integration exemplifies the convergence of electrical engineering, computer science, and environmental strategy, reflecting the complex requirements of a modern, sustainable energy ecosystem. Solar panels on rooftops, wind turbines along coasts, and smart grids linking regions together form a picture of energy that is adaptive, distributed, and environmentally conscious. Renewable sources, once limited by technology and cost, now contribute significantly to global electricity supply, demonstrating the capacity to replace or complement traditional systems. The shift toward clean energy represents an ongoing transformation in how societies generate, manage, and utilize electricity, continuing the historical trajectory of innovation that began with the earliest experiments in harnessing nature's forces. In specialized laboratories around the world, scientists replicate the reactions that power the stars, aiming to create energy through nuclear fusion. Unlike fission, which splits atoms, fusion combines light nuclei, such as isotopes of hydrogen, releasing enormous amounts of energy in the form of heat. Magnetic confinement devices, like tokamaks and stellarators, use powerful magnetic fields to contain superheated plasma, allowing temperatures of millions of degrees to be reached safely within the reactor chamber. The challenge lies in sustaining these conditions long enough for the fusion reaction to produce net energy, a feat that has driven decades of research and experimentation. Glowing plasma arcs swirl under the influence of magnetic fields, producing energy without the long-lived radioactive waste associated with fission reactors. Lasers and inertial confinement techniques provide an alternative approach, compressing fuel pellets with extreme precision to initiate fusion reactions. Instruments record temperature, pressure, plasma density, and energy output continuously, guiding operators in refining control methods and improving reactor stability. The work requires a combination of physics, materials science, and engineering innovation, as the components must withstand intense heat, radiation, and electromagnetic forces while maintaining integrity. Over repeated cycles, the promise of fusion extends far beyond the laboratory. If successfully commercialized, it could provide nearly limitless carbon-free electricity, transforming energy availability across the globe. Fusion does not rely on fossil fuels, produces minimal long-lived waste, and offers a high-energy density source capable of meeting the demands of growing populations and industrial expansion. Cities, industries, and transportation systems could access abundant electricity with reduced environmental impact, redefining the possibilities of human development and energy management. Experimental reactors around the world, from ITER in France to national facilities in the United States, Japan, and China, demonstrate both progress and ongoing challenges. Engineers focus on superconducting magnets, vacuum containment, and precision diagnostics, ensuring that plasma remains stable and energy gains exceed the input required to initiate the reaction. Each successful test increases understanding of magnetic confinement, fuel cycles, and energy capture, contributing to the eventual goal of continuous, safe, and efficient fusion power. Fusion also represents a culmination of centuries of energy exploration. From the earliest experiments with static electricity to the large-scale turbines, hydroelectric plants, and nuclear fission reactors of the 20th century, humanity's pursuit of energy has been a continuous journey of innovation. Fusion builds on this history, integrating knowledge of electromagnetic principles, high-energy physics, and material resilience into a next-generation technology that could redefine energy systems. Looking ahead, fusion energy envisions a future where cities glow brightly without reliance on fossil fuels. Industries operate efficiently with minimal ecological impact, and energy scarcity becomes a challenge of the past. The research underway reflects a blend of human ingenuity, technical precision, and the enduring curiosity that has propelled scientific progress for centuries. Fusion represents more than a technological achievement. It is a bridge between fundamental physics and the practical demands of civilization, offering a source of electricity capable of sustaining generations. Beyond the laboratory, the promise of fusion could reshape global energy systems, creating opportunities for decentralized, resilient grids that integrate with solar, wind, and other renewable sources. Nations could achieve energy independence while reducing carbon emissions, fostering environmental recovery, and mitigating the effects of climate change. Communities may benefit from reliable electricity in ways that enhance education, healthcare, and economic development, while industrial innovation could accelerate with abundant, high-density power. As fusion progresses from experimental reactors to functional energy systems, it offers a profound vision of a sustainable future where human ambition aligns harmoniously with the forces of nature. Rivers may flow freely without diversion to turbines, mountainsides remain untouched by mining, and skies grow clearer as the reliance on combustion fades. Schools, hospitals, and homes could operate with uninterrupted electricity, while scientific facilities expand their reach, powered by this abundant energy. In this world, the pursuit of knowledge, creativity, and innovation may flourish unbounded, as the constraints of energy availability are replaced by the near-limitless potential of the atom united. Fusion, in its essence, is not just about energy, it is about possibility. It embodies a moment in human history when the mastery of fundamental forces converges with imagination and responsibility, offering a canvas upon which civilization can paint a future defined by sustainability, resilience, and discovery. As our journey through the evolution of energy comes to a close, allow yourself to sink even deeper into relaxation. Feel the soft hum of turbines and the gentle flow of rivers that have powered communities, as if the very pulse of civilization is settling into your body. Let the memories of glowing lights, quiet machinery, and the serene landscapes of renewable energy envelop your mind. Your thoughts can drift freely, your muscles soften, and your breath flows effortlessly, carrying you into a place of calm reflection. Rest here, fully supported in this safe and serene space. If you enjoyed this relaxing moment, please consider leaving a like, subscribing, and turning on all notifications so you don't miss any of our future videos. But for now, let your body relax, release any tension, and allow your mind to drift. Good night and sleep well.